So the addition of strong acids and bases to buffers, this is what I was talking about before, where if you add a strong acid or a weak base or a strong base to a buffer, it's going to be neutralized by the weak conjugate base or the weak conjugate acid. And that's how a buffer really works, is that it works by neutralizing the strong acid, the strong base that you get added to it. So it doesn't really affect the pH of it. And since you have the conjugate acid and the conjugate base, the buffer is good for neutralizing both acids and bases. Consider the acid-base neutralization reaction. Step is a limiting reactance stoichiometry. You don't really have to worry about that. Use the calculated value of HA and HA minus or A minus. Step can be, okay, so again, you might have to use the Hasselbalch equation, which is on your reference table. Just plug into that after calculating for Ka, pKa, and for the concentrations of the conjugate base and the conjugate acid, and you should be good for that. Moving on, acid-base titrations. You don't need to really worry about that for now, so I'm going to skip past that. All you need to know is that the equivalence point is the point where it's going to have a greater concentration of, let's see, OH or H plus or whatever. That's where it's going to change over. So if you have an originally acidic concentration of something and you add a base to it, the point where it becomes past a certain pH, that would be your equivalent point. And if you have a indicator, you want the indicator to be around the equivalence point for it to work. That's really all you need to know. If the concentration of OH equals the concentration of H, and they all cancel out perfectly, then the pH of the substance is going to be 7, because that's perfectly neutral, since the concentration of the hydrogen ions equals the concentration of the hydroxide ions. So section 4, solubility equilibria. Equilibria we have considered thus far. Hold on, what is section 5 on? Factors that affect solubility. I'm just going to touch on solubility equilibria here because it's not too difficult. It's just basically solubility. So you'll have something like CaCO3. Oh, that's the wrong one. Erase that. Draw CaCO3. And that'll be a solid. And you're looking at how well that dissociates. So you got Ca plus 2, I think that is, plus CO3 minus 2. Yes, I know it's very sloppy, but it's very hard to write. And then both of these are aqueous, because remember, when it's dissociating into the aqueous ions. So remember, when you're writing the equilibrium equations, we don't add in things that are solids. So we write the equilibrium equation for this, and we got the concentration of Ca plus times the concentration of CO3 2 minus. So then that would be our solubility equilibrium equation for that. That's the important thing, knowing how to write it and knowing what it means. You can plug into it just like normal equilibrium equations. You take the concentrations of the 2 ions, and that's how you find your KSP. So this is another example here. They have barium sulfate. It dissociates into barium and sulfate, and you multiply those two together, because remember, barium sulfate's the solid. So originally it would be products over reactants, but because the reactants are only solids, they get left out. So you just have the 2 products being multiplied, and that's how you find your KSP constant. So there it is. There's the calculations right there. It's just more practice problems. Solubility and KSP. Solubility is not KSP. Solubility gets affected by many factors. Remember that any equilibrium constant is the same at any temperature. So know that common things that would affect solubility don't necessarily affect KSP. only temperature, only temperature, only temperature. Solubility effective. This is saying that what I just said. Limitation of solubility products. It's possible to use the conditions. So this is a way of converting from KSP to regular solubility. Basically just being able to know that you can convert between the two. So factors that affect solubility. I mentioned before that solubility is affected by many factors, but remember KSP being an equilibrium constant is only affected by one factor, and that is temperature. Only affected by temperature. We will examine the phenomenon of amphoterism, which is the way that pH and complexing agents affect the solubility of a ionic compound. So a salt solubility is affected by the presence of common ions, the solution pH, and the presence of complexing agents. Just know we're going to talk about those factors. Common ion effect. Remember, we talked about the common ion effect before. If you have a common ion, there's going to be more of that ion on one side. So what's the system going to try and do? It's going to try and reduce the number or the concentration of ions back to the original. So it's going to shift away from it. So you'll see that the amount of CaF2 in this case would be higher if you have a common ion, meaning that less of it is dissociating, meaning that it has a lower solubility. So if originally you had half of this dissociating, now because you have the common ion effect, it's going to shift away and increase the rate of the reverse reaction. And now maybe only 30% of it will dissociate. So you see that solubility there will be decreased in the presence of a second solute that furnishes a common ion. So common ions make it less soluble. Practice problems there. Solubility in pH. Talking about the metal hydroxides, KSP, saturated solution. If solid is equilibrium, pH. In general, the solubility of a compound containing a basic anion, that is the anion of a weak acid, increases as the solution becomes more acidic. So again, this is just intuitive. You have Le Chatelier's principle saying that you want to shift your equations in order to reduce the stress on a system. So if you're making it more acidic, the system is going to shift to make more of something that's basic, okay? And if you make the solution more basic, the system wants to shift in order to make it more acidic, okay? And that's all that's saying. You make it more acidic, it's going to make more of a basic anion. Other salts, the solubility of slightly soluble salts containing basic anions increases as the pH is lowered. Again, solubility containing basic anions. So, what did I just do there? As the pH is lowered, so if the pH is lowered, it becomes more acidic. So if it becomes more acidic, then the solubility of something, the solubility of the basic salts will increase because they're basic. You made it more acidic and it wants to get back to where it originally was. So it's going to make more of the basic ions. Sorry. Formation of complex ions. So let's see if they have a good definition for a complex ion here. Characteristic property of metals is their ability to act as Lewis acid toward water molecules, which acts as Lewis bases. So it's the way that certain metals can react with water in this case, or other substances. So something like AgCl, which is a salt, combination of silver chloride, dissolves in the presence of aqueous ammonia because, complex ion is when a salt will dissolve in something other than water. Right? Or whenever a metal is dissolved in something. So it'll be water, it'll be ammonia, anything like that. You'll see these reactions occur. So for a Lewis base such as ammonia, to increase solubility of metal salt, the base must be An assembly of a metal ion and a Lewis base bonded to it, such as silver, ammonia, is called a complex ion. So the combination of a base and a metal is a complex ion. That's what a complex ion is. And that's formed when you submerge the salt that has a metal in it to something that is a basic solute, because the solvent's the thing that goes in it, I believe, or maybe it's the reverse. I'm not 100% sure on that. Note that the equilibrium constant of the combination. So these are just basically all equilibrium equations, and just knowing that the complex ion is a silver plus a base, and being able to derive that is basically just using your equilibrium rules. General rule for solubility is solids increase in the presence of more suitable base. Okay, so the more of a base, the more soluble the metal salts become, because they can form those metals base molecules. Amphoterism, amphoteric oxides and amphoteric hydroxides, metal oxides and hydroxides that are relatively insoluble in water dissolve in strongly acidic and strongly basic solutions. So you'll have some things that won't dissolve in water, but they will dissolve when you put them in strong acids and strong bases. So why does that happen? We'll look at the effect here, but know that those are amphoteric oxides and amphoteric hydroxides. Obviously, it's a oxide if it's a metal and oxygen, and a hydroxide if it's a metal and hydroxide. Like other metal oxides and hydroxides dissolve in acidic solutions because their anions, O2 and OH, react with acids. So these things that the metals were originally bonded to will react with the strong acids in order to react, and they will dissociate into what is soluble ions. So you'll see it here. You'll have the original substance, aluminum hydroxide. This was not originally soluble in water, but you add it to something that is a base that has the OH aqueous solution in it, and you'll get an aqueous product. So that's the whole point of the amphoteric oxides and amphoteric hydroxides, is that it's a way of making things that are not generally soluble in water, soluble in strong acids and strong bases. Solutions filtered to get rid of ion impurities. This is just general uses for it. Okay, section 6, the precipitation and separation of ion. Determine the conditions that lead to precipitation. Equilibrium can be achieved starting with substance on either side. Remember, you can start with either substances on either side. That's how equilibrium works. Call that the reaction quotient Q. So remember, Q was basically the same thing as the equilibrium equation, except instead of using your equilibrium concentrations, you're using your initial concentrations before you reach equilibrium. Q is greater than K, product concentrations are too high. This is all from chapter 15. If Q is less than K, then your product concentrations are too low. If Q equals K, it's at equilibrium. For solubility product equilibria, the concentration between Q, KSB is exactly like that for the equilibria. So again, these are the same rules. If Q equals KSP, so the constant for the solubility product, it's at equilibrium. If Q is less, then the product will proceed to the reaction will proceed to the product side, so to the right, because remember, it's products over the reactants. So if there's a little Q, that means you got more on the bottom, less on the top, and you need to make more on the top, so it's going to shift to the right. If you have the reverse and you have a Q larger than KSP, then you have too much on the top and it's going to shift to the left in order to form more of the solid and lower that Q value. For the case of the barium sulfate solution, we would calculate Q equals that times that. Okay, that's just an example. So moving on. Selective precipitations of ions. Ions can be separated from each other based on the solutions. So these are just talking about that certain ions can be separated based off their properties. And this is more used in the real life world. because as we talked about, some substances will only dissolve. And when I say dissolve, I mean dissociate into ions in certain acidic and certain basic substances. So if you're trying to remove something from a metal or some sort of substance, you can put it in a solution of certain pH and it'll successfully dissociate and leave you with the parts that you desire. And this is just talking about examples. And that whole process is called selective precipitation. Forms of precipitate with more. Yeah, ions can be separated from each other based on their solubilities or their salt. Consider a solution if HCl is added. So this is just talking about something being added and it's separating only into what you desire. So if you have a substance like AgCl and you add hydrochloric acid, remains in solution because you can separate the HCl and the Cl2 if you want. It's a way of getting rid of something chemically that you can't normally separate physically, mechanically. So that is all we need to cover.